Hello, welcome back. It's been a long time actually since I've done the last video, so for me it's like I'm starting again making videos, but for you I guess just the next video on the playlist, which is fine. So yeah, it's been a couple of months actually since the last video, and during those 2 months I've been finally making some progress on the meshing part. So on all the past videos I've been like on a broken record, saying like, yeah, this looks terrible, it's just debug boxes, I have nothing visual to show. So now I can finally stop saying that, because now, as you will be able to see, yay, we have some meshing going on. So now our chunks actually look like chunk with actual blocks, and yeah, it's still ugly, obviously. I would give you that, but at least it's just not debug boxes. We can bring back the boxes if you really want. We can bring back the boxes. Don't worry, we can bring back. Yay! The debug boxes are back. Now let's just stop that. Yeah. So yeah, this video is going to focus on the basic meshing of the chunks. And so now I relaunched the project and it looks identical to what I was showing before. I would just want to talk about 2 different way of meshing chunks. So the first way I'm going to show right now, I have disabled the what we call the greedy meshing. So now what we're seeing is the naive meshing basically. So each block, each face, I should reduce the speed of the camera a bit here. So each face of each block is 2 triangles. So 1 quad, 2 triangles. By the way, just before talking about naive meshing versus greedy meshing, we want each face of the cube to be to have its own set of vertices. We don't share vertices between faces. I'm going to stop moving the camera and draw over the screen during the editing and show you what I mean by that. So basically, right now what we have is that each face of each cube has its own vertices. We do not share the vertices, and the reason is for the normals. We want to tell the GPU that each face has different normals, so it's shaded properly as we expect. In some cases, like depending on the look that you want, you might be fine in some cases to just have merge vertices, so you can cut back quite a bit on the number of vertices and polygons to manage. But it's a different look, so yeah, it depends on what you want. I'm not talking about the LOD yet, but it's something I could be doing, for example, for LODs, like maybe in the background, I would not care about having proper shading for each face. I could just merge all vertices maybe and cut back on the number of vertices, but I'm not doing that right now, and the LODs are just so fast to mesh and so light already that I won't bother about it. And by the way, talking about speaking about LODs, yeah, I won't talk about them in this video, but they will have their own video, probably the next one actually, because yeah, it's a topic that deserves its own video. It's interesting, I think. But anyway, yeah. So now if I show you the wireframe, no, not like that. If I show you the wireframe, so as you can see, the naive meshing is each face is 2 triangles. It doesn't matter what the blocks are. Each face gets its own triangle. It's the most straightforward meshing. It's also the least efficient in a sense, because yeah, you have two triangles per face. But we can do better than that, and I'm going to show you how we can do better. But before showing you the greedy meshing, which is the optimized version of what I'm showing right now, you might also notice that if I go in here, so if I go inside, as you can see, the blocks, like I'm obviously not meshing all faces, like the 6 faces of the cubes, right? But it sounds obvious for many of you probably, but when you are a beginner and you want to do this kind of games, I mean, I don't know about you guys, but this is what I did a long time ago when I first approached this issue. I just, instanced cube, and it's a cube, so I want cubes. But no, what you actually care about is just what you can see. Because right now I can go inside the map, but the player will not be able to do that. So what you see right now is what you mesh. You don't want to mesh any face that is invisible. So I'm going to probably to put something to show this, like to illustrate this maybe a bit more. So yeah, not only you don't generate all the blocks, but you don't mesh the faces that are invisible. So it's not just a block optimization. Like obviously I'm not meshing all the blocks that are inside the chunks, but it's not enough to optimize that. You also want to just draw the exact faces that you anyway, so that's just the very basics of meshing a blocky map like that, a voxel. I won't be talking about voxels because technically they are not voxels. I know that some people like to use that, but I'm kind of a pedantic guy. I won't say that. I will call it cubes or blocks. All right. So enough talk about the naive meshing. We don't like naive meshing. It's bad. No, it's not true. No, it's a fine solution in some cases. But the thing is, with the gritty meshing I'm about to present, not only it's going to generate less vertices and less triangles overall, but it's also faster to run. So there is really no point in using naive meshing when you have an efficient gritty meshing algorithm. So I'm going to just have to relaunch the engine and enable gritty meshing. All right, and so we are back, and from the outside, it's going to look exactly the same. Like the result is the same. The gritty meshing obviously gives the same result. But now if I switch to wireframe, you're going to see that actually, the faces are optimized. And as you can see, many cubes faces have been merged together. And so it's I mean, in some cases, as you can see, it gives the same result because we are in an area where we can't really merge stuff. But in other places, like you can obviously see how much more efficient this is. It's going to reduce the amount of vertices. One caveat to mention, which is obvious, is that right now all the blocks are the same boring gray blocks. But in the future, like you might have some blocks that are like dirt and some other blocks that are stone. So you can obviously only merge the faces of blocks that are of the same type. You can't merge like a dirt block face with the adjacent stone block face. So right now it's more efficient than it will actually be in an actual map. But anyway, it's still going to be more efficient. And so now I'm going to explain meshing, especially gritty meshing, but not just that. Before we start, I think it's important to understand how we are structuring the chunk data. And so what we're seeing right now is just basically a quick representation of a chunk, a full chunk, like full of blocks. And so yeah, this is what a chunk is. It's a 3D cube containing blocks at regular intervals. And so you could go around this many ways. Like you could have a 3D array basically, or like when I say 3D array, I include like one-dimensional array with 3D indexing, so just a flat list of data that you refer to. And this is fine. This is this is the most straightforward thing. It's the first thing you think about. But I think, and especially for meshing, as we are going to see during the gritty meshing algorithm, it's important to really think about what's more convenient. And in my case, I've been doing pillars of blocks. I maintain this array. It's not actually an array. In my case, it's a map of blocks. I maintain this map of blocks on one side when I need to refer to a specific block. But when I need to know whether a face or not, a face of a block needs to be meshed or not, I'm actually using a mask, which is basically a presence map. A presence mask. It's a quick bitmask that tells me whether a block is solid or empty. And so I'm using for that unsigned integer, 64 bits unsigned integer. So each pillar that you can see on this chunk is actually encoded as a 2D array of 64 unsigned bits. And so this means that, so as a side note, this means that the maximum chunk size is 64. So I cannot have more than 64 blocks in one dimension. I mean, in the height, the Z dimension, which is fine. It's actually the size of my chunks. My chunks are 64 by 64 by 64, and it gives a good speed for meshing and also for the memory. It's a nice compromise. So I'm happy with that. And so as you can see, each of these uint 64 is encoding whether a block is empty or solid. So hopefully with this illustration you can see. So when I have a 0, when I have a 1, it means that the block that we are seeing is solid, and when I have a 0, it means that the block is empty. So why we are doing this? It's very simple. Like as I was mentioning previously, we only want to mesh the faces that we actually see. We don't want to mesh all 6 faces of each block. That would be too expensive and actually slower. So why not save mesh? Why not save resources and be faster at the same time? And so I think to illustrate how we define which face is visible or not, we need not just one of these pillars of presence mask, but 2 of them, just so we can see how it goes. And so yeah, so this is just an example with some random blocks that are solid and some other that are empty. And so in this configuration, we're looking at the leftmost pillar, and we want to mesh the face that are facing screen right. And so we need the adjacent pillar to know that. So the adjacent unsigned integer. And so yeah, if we take a look at the one on the left, we have 0 where blocks are empty. So yeah, first of all, we can just skip empty blocks. We will never mesh an empty block and a block. So we only care about the ones. And so we want to know if these faces that are highlighted right now should be meshed or not. And so to do that, we just need to look to find the adjacent pillar that is represented on screen right. And so when we take a look at that, we can just simply take a look at the status, the 0 and the 1s on the adjacent integer. And so when we have 2 1s, that means that the face cannot be visible because the face is hidden by the pillar on the screen right. Same for the one above. And so we know that these faces can be skipped, and all the other faces highlighted in green right now can be meshed because they are facing empty blocks, so they are potentially visible. And so so we end up with this face and this face can be skipped, and so only these faces that we are seeing right now should be meshed. So this is the theory, and so I mean you don't need bitmask structure to do that. You could just go on the blocks one by one. Is this adjacent block visible, solid or empty? Yes or no, and go one by one. But that's kind of slow, right? So the advantage of using 64 bits right now like that is that we can use bitwise operation. So we can basically very, very quickly know if the 60, like we can check 64 faces at a time, which is obviously much faster than 64 blocks one by one. Yeah, so hopefully you understand the advantages of this technique. But yeah, I think I needed to show this before showing the greedy meshing. because yeah, this whether you use greedy meshing or naive meshing, this doesn't change. I think it's worth holding this extra. It's a 2D array of integer of 64 bits integer. It's not completely free in terms of memory, but it's quite cheap, and I think it's very useful, and it's speeding the machine quite a bit. And this presence mask can be used for many things. Like for example, it's very useful for collisions as well. Very often for collisions, you don't need to know the exact block type. You just need to know whether the block is full or whether the block is solid or empty. So this is like a flexible data that can be used for more than just meshing. So yeah, that's why I'm doing this, and I think it's super useful. It's super useful for any kind of collision detection, that kind of stuff. And obviously, I've only been showing like one axis right now. I've only been showing like one pillar, checking one adjacent pillar. But you need to do this on all 6 axes for each face. But yeah, just for the sake of the example, I was just showing one. And so yeah, 3D meshing. So now that you know a bit more about how we define which face is visible and which face is not visible. Now we can talk a bit more about 3D meshing. And so what you're seeing right now is basically a chunk where I just removed random blocks inside. And so we're just going to care about one slice, as I was mentioning previously for the example with the solid presence mask. I'm just going to show one slice and one axis, but you need to do this 6 times basically for all faces of the blocks. This step can only start after we defined which face should be meshed or not. And so at this point, you just run through every face. The one highlighted is the first one. And so now we are looking, we're going to expand this face. So the greedy meshing is all about merging face together as long as we can. So as long as the next block is the same type and has a visible face in the same axis, like facing the same coordinate, the same direction, we should be able to merge. So the first step in the algorithm is just to look ahead. So the next block, the block just above, does it have the same type, and does it have a face facing the same direction? In this case, yes. So we can extend the mesh, the face, and then next iteration again we look up. Is there a block? In this case, there is no block, so we stop here and we can just finish this face. So this face is done, and in this particular case, we only expanded in one axis, but we can expand in 2 axes the faces. I'm going to show that just after. And so now next block is next face to mesh is the one here that is now highlighted. And so yeah, again we look up next block up. We can merge, next block up, we can merge, next block up, we can merge, and boom. We have to stop that. As I was saying, we could have maybe expanded in the other axis, but the very first face that we started the face with, the mesh face with, cannot expand on this axis, right? So at this point, this current face cannot have a width of more than one face. So yeah, that's why we can only expand now in this one axis. Again, I'm going to skip, and yeah, next one, pretty obvious. So now actually this one we cannot expand up, as you can see, because we reached the end of the check. So now that we cannot expand in this direction, so we look at the other direction. Can we expand? Yes. And so boom, we have this face. And again, this one is done. So we stop here and we add the quad to the mesh data. And so yeah, we can go. Yeah, I'm just going to skip a bit. Yeah, we can see how this is going. And now we arrive at this one. So this one is interesting because yeah, we start here as always. We look up. Can we merge? Yes. And now we cannot merge up anymore, but we can merge two faces at a time because the other axis can have these faces merged. And so boom, we have a big square now. So this one is just one quad instead of 4 with the naive meshing approach. So yeah, that's quite nice. And so yeah, and so on. We can just continue merging all the faces. Again, this one. And so yeah, as you can see, it's quite simple to understand. It's just merging the faces together. And so at this point, this slice is done. We can only ever obviously merge face in the same slice. We can't, have a face cross multiple slices and be merged with a block that is behind or whatever. So yeah, it's really per axis. And so yeah, this is the result. And as you can see, yeah, all these merged faces are just single quads, so 2 triangles instead of 2 triangles per face. So we're doing almost the same job as the naive meshing, but along the way we're just keeping track of a couple of width, length, and that's it. So it's actually not more expensive. It's actually cheaper than naive meshing. So yeah, it's worth doing it. And so this is the view with the full chunk. And so yeah, that's it for the 3D meshing. So I'm not going into detail. I will be linking a repository. So it's something I was doing before, and then I found this GitHub repository, which is actually doing a better job than what I was doing. So I implemented something similar. I really highly encourage you taking a look. It's using the same bitmask thing I presented before, and yeah, I implemented a similar algorithm, and it's quite nice. And so one thing I wanted to mention, so maybe when I was talking about the faces, you might have noticed this face, this couple of faces here, that you might be tempted to think that it's suboptimal. Like you feel like, yeah, we can have a big quad here instead of just two long faces like that. That when you look at that, you feel like it's wrong. Like it looks wrong. It should be better. Like we could do better, right? We could have this big one here, and it would be nicer, right? But I mean, if you look at the end result, it's actually the same. You just end up with 2 quads. So yeah, this is the first version, 2 quads, and this is the version that instinctively you would want to have, but it's still 2 quads. So it's actually the exact same cost. So you're not gaining much by trying to be super optimal. I'm sure the algorithm I'm using is not optimal. I'm sure if you really wanted to and you are really smart, you can come up with a nice algorithm that will give you the exact optimal quad number for this chunk. But I really don't think it's worth the hassle, honestly. This method gives good enough result, and you could be gaining a few quads here and there, but it's worth it in my opinion. So yeah, quite easy algorithm actually. Again, right now we are merging all faces basically because all the blocks are the same type. They're all the gray blocks, but in an actual chunk you will often have different types of blocks, so you cannot merge blocks that are of a different type. All right, and actually it's a nice segue to the next topic to end this video. Yeah, because this video is going to be quite long, sorry. So the next topic is ambient occlusion, because we are baking ambient occlusion information in the chunks, and this also has an impact on whether we can merge a face or not. And so ambient occlusion, yeah, it's actually kind of hard to see right now because I have Lumen global illumination. So Lumen actually does a good job of kind of giving the same result as baked ambient occlusion. So you might wonder, like, yeah, is it worth baking ambient occlusion? I mean, I might disable Lumen anyway. So yeah, I think it's worth just having the option at least. But yeah, if I go to an inlet mode, so without lighting, now you can see that I'm baking ambient occlusion in the mesh data, so in the vertex color. As you may also be able to see I'm not doing that in the lower LOD meshes. I'm only doing this on the highest LOD because it doesn't have a zero cost. Like it's not entirely free. It's cheap. It's quite cheap, so it's not bad. You know, you can implement it, but it's not free. So especially when you have a super efficient algorithm, it's kind of almost doubling the cost. Not quite, but when it's super fast already, you need to compute a few more things. So yeah, I'm going to explain that in a bit. But yeah, as you can see, it's again, we just have gray blocks right now, so it might not be super helpful to really see the effect. But you know, without that, it does add a nice effect. I think when we have texture or more colors, it will be more obvious. But yeah, so now I'm going to explain how to do it. And so first of all, I think it's important to mention that this article is quite popular, I think, for this, and so I will give the link in the comment, in the description and in the article. But yeah, I mean, this is a very nice read. I'm basically going to show this. I didn't invent anything. Yeah, so yeah, please go and read the article. And so yeah, ambient occlusion, we're just going to look at an example with just one block. I'm just going to cover one vertex. So we compute the ambient occlusion per vertex, and it's entirely dependent on the adjacent block, not just all blocks, just the ones that are in the level above. So for example, in this case, let's take a look at this configuration. And so the only vertex that's going to interest us is this one. And so yeah, so for all the next images, you just have to ignore all the other vertices. We are only carrying back this one for only for the block at the bottom of the screen. And so yeah, let's take a look. So this one has an adjacent block on the top right, and I'm just going to disable the wireframe. And so now we can see that this is the ambient occlusion that needs to be computed. So it's just a float value in this case, between 0 and 1. And so in this case, when you just have one side neighbor, like one side adjacent block, solid adjacent block, you basically have a value 1/3. And it's the same for the other side. It's exact same configuration, so 1/3, and as well as the block directly in the corner of this block. This one might be harder to see, so I just if we just add the two other directly adjacent block, yeah, this is how it looks. So now hopefully you can see, and yeah, if we add the wireframe, this is how it looks. Yeah, so this is like the first, so these three configurations, the two sides and the corner, is the first configuration. So this gives the lowest ambient occlusion. Actually, no, that's not true. The actually lowest ambient occlusion is 1, so it's when it's fully like it's just the block by itself without any blocking adjacent block. But yeah, the next one is this configuration. So either one of the two sides or the corner block. And so let's take a look at the next configuration. So we go back to this configuration with one side, and we just add a corner block. And in this case, the ambient occlusion is going to be actually 1/3. The ambient occlusion, like 0 is maximum occlusion, and 1 is no occlusion at all. As you can see, it gets darker because this vertex is occluded by more stuff around it. Basically, it's the same. Like the mirror is the same. If it's the other side, it's the same result, obviously. And so now we are going to take a look at the last configuration, which is the maximum occlusion. It's when you have either 3 neighbors like this one, and then yeah, now it's the darkest value 0, maximum occlusion. And so this also you don't need the 3 blocks. Only 2 sides is enough. So if you have 2 sides, or if you have a corner as well, it's just 0. And so all these can be translated in a very simple function. Again, please take a look at the article I mentioned before. Everything is explained here, but I'm just going to put it on the screen just as a reference. But it's actually, yeah, quite easy. I was saying it was a float, but in truth, usually what you end up doing, not always, but usually, is that you write this into the vertex color, which depending on what you're using, if you're using an engine, for example, it will be a byte, so 8 bits. So it's the float. You just have a value between 0 and 255. But that's pretty straightforward. All right. And so one last thing is that on all these images about ambient occlusion, I've only been showing you for this one vertex that I was talking about, the one for the bottom block. But obviously, what we're showing right now is not correct. All the faces and all the vertices, yeah, they compute their ambient occlusion. So for example, if you take a look at this block that's highlighted now, it will basically have the same result because of the bottom block and the side block. So it will give you the same 0 ambient occlusion. And same thing for the last block, which also has 2 sides, two side neighbors. So yeah, same thing. But as you can see now, something weird is happening because it's not symmetrical. So we just said that all 3 vertices for these 3 blocks have the same ambient occlusion value, and yet it doesn't look symmetrical, which is strange. But if we put the wireframe including the triangles, hopefully now you can understand why this is happening. So this triangle is not, it's not the same triangle configuration, right? So the 2 blocks on the left and on the bottom, they get the same visual result because they have the same triangulation, but the interpolation is not the same for the one on the right. And so the easiest way to fix that is to just flip the triangles, and if you do that, boom, you have a nice symmetrical ambient occlusion. Again, check the article I linked, and everything is explained again. You just have to check for the ordering of the vertices. It's quite simple. All right, so I think that covers it for the ambient occlusion, and I think that covers it for this whole video. I think it's going to be quite long. Lots of information, most of it available already on the internet, so nothing new really, but yeah, it's just something I've been doing for my project, and it's done. And yeah, next video I will be talking about LODs, and yeah, see you next time. Something I forgot to talk about is a detail. That's quite important actually. So the chunks, you have a defined chunk size. I was talking about 64 by 64 by 64, but actually not all of these blocks are meshed. What I mean is that I'm using an extra border, so the one block in the border is actually not meshed. It's only used for ambient occlusion, and so I just disabled this to show you the issue. So this is the unlit version, so we can see the ambient occlusion. And as you can see, when we switch chunks, the ambient occlusion fails because right now all the chunks only know about their blocks, and they don't know about the adjacent chunks. So they don't know whether the next block is solid or empty. So basically the ambient occlusion is null. So which by default means there is no occlusion. So that's why we have this very visible seam between each chunk. And so, yeah, I'm just going to give a quick illustration of that. All right, so this is a chunk, very simple representation of a chunk. And right now, all these orange blocks mean that these are meshed. And so, yeah, this chunk doesn't know about the adjacent chunks at all. So they can't really figure out whether the adjacent blocks are empty or not. So not only for ambient occlusion actually, but also for checking whether a face should be meshed or not. It's important. So if you don't know if the next chunk, what the next chunk contains, so if you don't know what the next block at the border is, you can't know whether you should draw a face or not, or whether you should consider this as occluded or not. And so what we do is that all the border blocks are in blue in this image, which means that they are not meshed. They are only used for occlusion purpose. And I mean, obviously, you can't right now. You can't see well. So I've made this little animation for you, so you can see. So now, as you can see, as I drag the slice, you can see that inside are the orange block, which are the blocks that are going to be meshed. But the outskirts of the chunks, the one block border is actually not meshed. And so this is just another image from the top. You have to imagine that we are in the middle of the chunks, and so yeah, this is how it looks if we had a 2D chunk, for example. This would be how it looked. Yeah, so it's quite important. So from a programming standpoint, it doesn't change much. It's just you generate one extra block before the origin of the chunk and one extra block after the origin of the chunk. So what we saw today in this video, when we saw the meshes, we actually saw 62 by 62 by 62 chunks, even if each chunk actually contains 64 by 64 by 64 blocks. What we can see is actually just 2 blocks less than the actual size of the chunk, and it's pretty straightforward to work around this. You just have to adjust the position of the meshes in the world, blah blah blah. But it's all pretty straightforward, so I won't really talk more about it. But it's something I forgot to talk about today, and it's quite important. It's an easy fix to an annoying problem, because there are other solutions. If you really don't want to generate one extra block for each chunk, you could wait for all the chunks of an area to be generated, then each chunk will need to then query for some information about the data of adjacent chunks. But as you can probably imagine, it's extremely painful. So this quick, just generate an extra block for chunks. It's actually super easy to do, and it solves the issue. And yes, it does mean that you are kind of generating a few blocks more than you could get away with, but yeah, it's a small price to pay for such an easy solution. All right, yeah, I'm done for good. Yeah, this video is way too long. Bye bye. See you next time.